Our next session is going a bit different direction with Johann. Johann is a graduate from Hochschule Bonn-Rhein-Sieg, I think on the honors. Anyway, Johann is going to talk about Narrowband IoT and DTLS, if I understand correctly, and there's a lot of electronics appearing here. Yeah.
Okay.
We need some more.
Great. Okay. Very nice. So thank you. Yes, I'd like to present the results of my bachelor thesis that I completed a couple of months ago. And the title was Performance of DTLS with Connection ID over Narrowband IoT. It's supposed to work.
Except it was working a second ago.
Yeah. Okay. Don't have
Just find a plug in this one and then
let's try this one.
and there should be one in front of.
Let's try that.
Hey.
Okay. So yeah. So we're looking at communication in IoT networks. We want it to be encrypted, and we also want it to be efficient. We're using DTLS as the protocol to establish an encrypted session. And there is an issue with port and IP changes during active communication, which leads to the communication, the session being abandoned and having to restart. And a solution for this problem was developed. It's called Connection ID. And I was looking at the benefits of Connection ID. In reality, what in terms of power consumption as well as timing does it actually save? So yeah, we have an IoT client. This is a Nordic 9160 development board that I was using. And that IoT client is connected to the internet over Narrowband IoT. So my development board has a SIM card plugged into it and connected to the cellular network. And it wants to establish an encrypted session via DTLS. DTLS, you might be familiar with that. It's a variant of TLS running over UDP. And it's the client is sending a message to the server, and the server responds with an acknowledgement. Now, the default behavior in DTLS is that when the client sends a message to the server, how does the server identify the packet belonging to a specific session that was negotiated before? Because the server might be handling more encrypted sessions with different clients, and the server looks at the source IP and port of an incoming packet and then matches that to an existing session that it knows. So that leads to a problem. Well, what happens if the IP address or the port of my client changes because maybe the provider assigns a new IP address to it, or the packet is traversing a network, it's traversing carrier grade net maybe, and the source port changes? Well, then the server can't identify the packet anymore, just doesn't respond, discards it, and the client will then start a few retries, and then eventually consider the connection as being lost, and then we'll have to start a new DTLS handshake. And to avoid that, to avoid a new handshake when IP addresses or ports change, this Connection ID extension in DTLS was actually developed. And that works in a way that during the handshake, a numeric identifier, this Connection ID, is negotiated. The server, for example, assigns that connection to the client, and then the client sends that Connection ID in the DTLS header with every subsequent application packet that's sent. So IP address or ports changes doesn't matter because the matching will happen according to the connection ID. So we avoid additional handshakes during when IP addresses or ports change. Okay, server verifies the connection ID and then can keep the connection active. So how do I measure the real benefits of connection ID? Well, I took a power profiler kit by Nordic Semiconductor, plugged it into my board, and then measured how much a DTLS handshake actually costs in terms of time, how long it takes to perform a DTLS handshake, as well as what's the power consumption of it, because that's what you would avoid if you were using connection ID versus not using it and having an IP or port change. So this is an example of measurement of one specific cipher suite. So we have, for example, this is DTLS 1.2. It's elliptic curve Diffie-Hellman. It's using certificates in both directions. The client has a certificate, the server has a certificate with ECDSA keys and using that NIST curve. So the first handshake that I measured took 7 seconds in timing. The electric charge that was consumed in millicoulomb was around 80, a little more over 80. The next handshake using the same cipher suite was about 90. And I was also measuring the peak current of all of those, as well as the sizes of the handshakes, the downloads and upload sizes. So average handshake time for this cipher suite and elliptic curve was 7 seconds. And now this graph is showing the average of different cipher suites. So I have one, that's the one we just saw on the very left, that the 7-second thing. The same cipher suite and curve in DTLS 1.3, so we see that's a little better in terms of performance. Then there's another elliptic curve, slightly better performance. And then, so the 4 on the left were using certificates, and the 4 on the right were using pre-check keys. So obviously the performance there is considerably better because you don't have to verify certificates. And now I was also including post-quantum crypto key share algorithms. So those are all in DTLS 1.3 now. And those 4 we've already seen, and this is comparing them with post-quantum crypto key shares. So this one, the big one here, that's using MLChem 512, but still with a certificate that's not post-quantum crypto, that's actually, that's ECDSA. So that's pretty similar to the cipher suite using NIST curve. And this I found interesting, that the performance of post-quantum crypto algorithms is actually pretty good. Is that the timing is quicker than it actually is with the non-post-quantum crypto key share algorithms. These are hybrid versions. So negotiating both post-quantum MLChem 512 key, as well as regular Diffie-Hellman keys. Yeah. Now, so we've just looked at the duration of a handshake, but there's also the power consumption of handshakes. It's around the 120 millicoulomb mark for those 1.3 DLS 1.3 key shares, and those are the post-quantum ones. And actually what I'd like to do is perform a measurement of a DTLS handshake live now. Yeah. This is turn the server on, and now let's reset the board. Now let's hope that, oh yeah, okay. Yeah. Yeah, so that's live measurement of DTLS application traffic taking place. So what, let's give this a pause. Okay, so what you just see here at the bottom, this is actually a DTLS handshake taking place due to a change in IP address, the source IP address of my client board. Because the traffic, the way I've set it up is that this board sends an application packet to a server, but there is a proxy in between, and that proxy changes the IP address on the fly with every third application packet being sent, and then the server doesn't respond. And then the client initiates a new handshake, and we can see this by this GPI opens I set in the application code there. And that's actually yeah, okay. So that's how long it took. I think that's, can anybody read this? I think this is around the 600 millisecond mark. And that's the electric charge that was being used. 23 millicoulomb is what this handshake took in power consumption. Yeah, and this is actually the cipher suite that I was using. It was actually a post-quantum crypto algorithm, MLChem 512. Okay. That's that one. Okay, so that was the way I was measuring these DTLS handshake and the cost that you could expect from IP address changes not using connection ID. So if you want your DTLS encrypted traffic to be more efficient, then I recommend you look at connection ID. Yeah. Okay. Yeah, so that's another slide showing traffic that the dark blue is showing traffic using connection ID. So with in these bars, you see how long it took for the client sending an application packet and the server responding to it. So the first one on the very left, you see it's about 90 milliseconds. The next one was somewhat more. And in the dark blue bars, you see that there was an IP address change in between, and connection ID actually connection ID was actually used, and the server verified it, and there was no handshake that had to take place. And that slide shows actually connection ID not being activated, and all of the extra power that's being consumed, that's the height of the bars, shows that the actual charging millicoulomb being used, and the time that took 12 seconds for the connection to be reestablished. In reality, it would be much longer because there would be retries, and which I wasn't using any retries. So the server when the server received a packet, it didn't know the IP address of, it would just not respond, and the client would restart a new connection immediately. Okay, that's another graph showing average power savings using connection ID in red versus not using connection ID in blue with each change of IP address support. And that would eventually translate to battery power being drained if you have many IP address support changes in your network environment. Okay, yeah, so that's the conclusion. Yeah, connectivity does bring improvements in power consumption and connection stability. We have to consider that too, that an IP address change wouldn't necessarily result in the connection being dropped. So I did see somewhat small improvements in DTLS 1.3 compared to 1.2. And I think the same thing, it's not necessarily bound to narrowband IoT. I think it can be applied to other radio technologies as well. So yeah, basically you want to keep your connection active even if there are IP address support changes, and maybe save a little power in the process as well. Okay, yeah, that will conclude my presentation.
Thank you, Johann.
Thank you. Okay.
The slide on, so.
Oh yeah. Oh yeah. Oops. Yes. Yes. Yes.
Okay. On slide 11, you had graphs on the handshakes. So if we go back to that slide.
Okay. That was this one. Yeah.
This one, yes. So basically you have on the legend like peak current in milliamperes with the blue dots. And the total charge on millicoulombs. Which is shown by the height of these dots.
Yes.
But on the Y legend you have values millicoulombs per milliamperes. I don't understand where these values are. So
well, the green is the millicoulomb and the blue is the milliamp.
sure, but where are those values of millicoulomb per milliampere? Where are those values? The ratio of those? Where are you showing those?
This is the blue one on the left. That's a little under 80 milliamp maximum peak current during a handshake.
Yeah.
And the green 80 something is the 80 millicoulomb electric charge used total for a handshake.
But where is the ratio? On the y-axis, aren't you trying to, or are you saying that? Oh, okay. So you are saying that y-axis is for both.
Yes.
Okay.
Yeah.
I got it.
Yeah. Yes. Yeah. Exactly. It's 80 either milliamp or millicoulomb.
Okay. Sure. Thanks.
Yeah.
It appeared to me like a ratio. I was thinking, where is it?
Yes.
Thanks, that was interesting. I would be curious about how often IP addresses actually change on narrowband IoT, because my impression, as not directly was that IP, at least IP over narrowband IoT would be IP6 anyway, so you're not running into carrier grade NAT and all those nasty business that plays IP4. So is that something that's common in narrowband IoT specifically compared to say Wi-Fi where you have recessed and versus IP4 nothing?
Yeah, I mean, narrowband IoT, the client connects to the internet via narrowband IoT, but the server, the packet then could traverse the internet connecting to a server through carrier grade net, for example, right? So for the server, for example, sits behind my Fritzbox at home, right? And it's like,
Okay, yeah.
yeah, yeah. And the other question, how often IP addresses changes in terms of the client side, where the provider assigns an IP address to the board, for example. I don't actually know. I mean, do you know?
Yeah, it's more like what changes. That's yeah. If you go through that, yeah. I'm not sure if your server is not bound. That yeah. No. So it's also sort of like a client being behind that. The client often sleeping. And if it stays a little bit longer, if the timeout is very low, it's actually changes almost thousands. I was thinking while there would be IP4 on narrowband IoT, but sure, if the server is before that, the client goes through all of versus everything.
Yeah. So yeah, this board now has an IPv4 address assigned, and I think it's changed. Does sometimes change. Yeah. Okay.
No more questions, then thanks again, Johann.
Thank you.